This is brought to you by the Alumni Association of PISJ-ES.
Hey guys, we're back again, and this time we'll be talking specifically about the acceleration time graphs. So let's see what they have got to give us. Acceleration time graphs. Now, with an acceleration time graph, the gradient of an acceleration time graph gives us nothing at all. So forget about this. For your case, the gradient of an acceleration time graph gives nothing to us. However, the area under the acceleration time graph gives us speed, or better, velocity. This gives us the velocity. So remember that we have seen a sequence here, kind of a sequence here. Let's see. For speed, a displacement time graph, the gradient gives us speed or velocity. And for a velocity time graph, the gradient gives us acceleration. So gradient is taking this to the right hand side. However, further after this, it's not of your concern, and this is not in your syllabus, so we'll just forget about that. After the gradient of acceleration time graph, we'll just forget about that. So the gradient of displacement time graph gives us velocity. The gradient of velocity time graph gives us acceleration. However, the reverse cycle is for the area under the curve. The area under the curve of an acceleration time graph gives us velocity, and the area under the curve of a velocity time graph gives us displacement. So it's going like this. So always remember it like this. Okay? So let's take an example here. A simple acceleration time graph, and these are for your IGCSE levels. These are very, very rare to be there in your questions in physics. So we'll still see a question here so that you get an understanding. And it's again a linear curve. We'll make a separate video for the nonlinear graphs, and we'll see how they're interpreted. In this case, this is the graph. This is a straight line, this is a straight line, and this is a straight line. This is an acceleration time graph. So this here it comes a/meters per second square, the units of acceleration. Here we'll write t/ the units of time, which is seconds. So this is the thing. Now I'm just taking some random readings here because we have been doing this particular shape of graph for a very long time. So we have always used this as 6, this is 2, this as 6, and this as 8. So from acceleration time graph, first of all we can talk about the acceleration of the object. Let's see. At point 0, at time t is equal to 0, the object has an acceleration of 0 meters per second square. This does not mean that the object is at stop. I told you before as well. This means that the object is at, it might be at stop, but not necessarily. It can be at a constant velocity, because we know that even at a constant velocity, we get acceleration is equal to 0 meters per second square. So it might be at rest, and it might be at a constant velocity. Now let's talk about this. The acceleration has increased with time, and at time t is equal to 2 seconds, the acceleration is 6 meters per second square. So the acceleration has increased with time, but we know the gradient of the acceleration time doesn't give us anything, at least at this level, so we'll just forget about this. We'll just see that it has increased to 6 meters per second square. Now from t is equals to 2 to t is equals to 6, it has a constant acceleration. This means that if the car had a velocity, remember that this does not mean that the speed is the same. No, it does. It means that if the car had a velocity of 20 meters per second at this point, the velocity will increase by 6 meters per second every second. So I can just predict at 3 the velocity would become 26 meters per second if this was 20 plus 6. At 4 the velocity would again increase by 6 meters per second, which would make it 32 meters per second. At 5 this would make it again an increase of 6 meters per second, so the velocity would be 38 meters per second, and at 6 it would become velocity of 44 meters per second. So this means the car is accelerating because it's an acceleration time graph. So this shows that the car is accelerating throughout this interval, and you can see the speed is increasing. So always make sure you are aware that this, you remind yourselves like 10 times before you are attempting a question that it's an acceleration time graph, or it's a velocity time graph, or it's a displacement time graph, and then analyze accordingly. Now from 6 to 8, you can see the acceleration at t is equals to 8 seconds is 0 meters per second square. Again, I can say that first, what is the kind of motion here? The car started and it was increasing its acceleration. At every second the acceleration was increasing. The first second there was an acceleration, for example, of 1 meters per second square or 3 meters per second square. The next second the acceleration was 6 meters per second square. The acceleration was increasing, the rate of change of velocity was increasing. That is what it was increasing. At 2 seconds, it maintained from 2 seconds to 6 seconds. It maintained a constant acceleration. So the car was increasing its increasing its velocity, but the acceleration was constant. As in, the change in the velocity was constant. It was always a 6 meters per second for every second. Change was constant, which is ironic again. The change is constant, but it is true. The change in velocity was constant, but we would say that it was still accelerating. And then it decreased the acceleration with time till it came t is equals to 8 seconds, and again it might have come to a stop because the acceleration is 0 or at a constant velocity. So this is the first thing we can find out about this. Okay, I don't think I need this because then my pointer becomes slow. Now for the same curve, let's find out. We have seen the acceleration. Let's find out what other information we can get from it. Let me draw the same curve again. This is 2, this is 6, and this is 8. In this case, this was 8. This is an acceleration time graph, so acceleration in meters per second square. This would be time in seconds. Remember guys, the formula of acceleration is equals to v final velocity minus the initial velocity divided by the time. So when we find the area under the curve, what are we doing essentially? We are simply, let's just imagine we're finding the area of the rectangle. What do? Base times height. So what are we doing simply? We're doing base times height. In this case, we are multiplying, or let's just say we are multiplying the x-axis with the y-axis. So the x-axis here is time, and we are multiplying this with acceleration in this case. So now let's just see, when we multiply time with acceleration, what do we have on the other side? Change in velocity, or in final velocity minus initial velocity. So the area under an acceleration time graph will give you the change in velocity in that particular time. For example, if the velocity was 20 earlier, and if the change is 6, the area under the curve is 6, this means that it will change from 20 to 26 and increase in the number, in the magnitude, by 6 meters per second. That is the change in velocity that we will get by finding the area under the curve. Let's see. Let's find the area under this curve, this part. This is a triangle, so whatever the velocity is here, we say whatever the velocity is here at point VA, whatever the velocity is here, point VB, we don't know the exact velocity. We do not find the exact velocity by the area under the curve. We only find the change between the two of them, the average change between the two of them. That is what we will be finding with this. So let's see what is the average change in velocity. So half times base times height for a triangle. So this would be half times the base is 2, the height is 6. This becomes 6 meters per second. So the average change in velocity during this interval is 6 meters per second. For example, if this was 18 initially, by this time this would have become 24 meters per second plus 6. So this is the average change that we are finding here, not the initial pinpoint velocity, no, just the average change. Now let's see what is the average change between VB and VC. If these are two velocities, two instantaneous velocities at two particular points, let's see what is the change. And to find the change in velocity, we find the area under this curve, this part. This is a rectangle, so simply the area of a rectangle is given by base times height. This is an A. So base this is 4, and the height is 6. So base times height would give me, change in velocity would be 4 times 6, which equals 24 meters per second. So whatever the velocity was at this point, this velocity is VB plus 24. An increase in VB by 24 meters per second gives us VC. The change throughout this interval is plus 24 meters per second. For example, if the velocity here was 20 meters per second, the velocity at here would be 44 meters per second. 20 plus 24 meters per second. Now let's find the change here in this interval. So again, we'll need to find the area of this, and let me just erase some of the things here. That I have some space here. So let me find the average change in velocity during this interval. So area under the graph. This is again a triangle. So half times base times height. So base is 2, height is 6. So half times 2 times 6. This is again 2 times, this is again 6 meters per second. The change in velocity between the points, let's say this is point D, between the time interval t is equals to 6 and t is equals to 8. When t is equals to 6 and t is equals to 8, the change in velocity between these 2 points would be 6 meters per second. For example, let's say, okay, we have all the calculations here. Let's say the velocity initially was 0 meters per second. Okay. Now we just calculated the first area, which was 6 meters per second. The answer was 6 meters per second, which means the change in velocity during this interval was 6 meters per second. So by this point, the velocity would increase to 0 plus 6 meters per second. The change is 6 meters per second. The velocity at this point would be 6 meters per second. Now, the change during this area, during this time interval, is 24 meters per second. This means that whatever the velocity here, we will add this with 24 to get the final velocity here. So, the change was 24 meters per second. It changed by 24 meters per second. So 6 plus 24, by this point, the velocity was 30 meters per second. And this, again, the area under this point gives us the answer, which is 6 meters per second. So again, the change in velocity was 6 meters per second. So the velocity at point D would be 30 plus 6 meters per second, which means the final velocity would be 36 meters per second. So guys, always remember that the area under the acceleration time graph is not the velocity, it's not the instantaneous velocity, it's not the average velocity, it's always the change in velocity during that interval. So if you have any queries, guys, just comment and I'll be replying to them, and stay tuned to it. Thanks for watching.